in this lecture, I am going to present what are the different steps used to determine the internal member forces of a continuous beam by flexibility matrix method. Then I would like to solve a 3-span continuous beam problem. Then coming to what are the different steps used to find out the internal member forces by the flexibility matrix method. These are the different steps. First, determine the degree of static indeterminacy or degree of redundancy. Then choose the redundant according to the degree of static indeterminacy. Then assign the coordinates 1, 2, 3 and to the redundant. Then remove all the redundant to obtain the release structure. Then determine the displacement delta L in coordinate direction due to given loading condition in the basic determinant and release structure. Then determine the displacement at the coordinates due to the redundant acting on the release structure delta R. Then compute the net displacement at the coordinates. This is equal to delta E is equal to delta L plus delta R. Delta L is the displacement due to the given loading and delta R is the displacement due to the redundant. Then the total displacement or net displacement delta is equal to delta L plus del into P. Delta R is equal to del into P. This is the flexibility matrix and this is the column matrix of the redundants. Then apply the condition of compatibility of displacement to compute the redundants. Then you can find out what is the redundant using the compatibility condition. So you have to take delta minus delta L and the del inverse, the inverse of the flexibility matrix delta minus delta L. So using this relation you can find out what is the redundant. Then after knowing the redundant, compute the internal member forces by using the equation of statics. Then after getting the redundants, then you can find out what are the internal member forces by using the equation of statics. So these are the different steps you have to remember to solve the any continuous beam using the flexibility matrix method. Here you have to remember, for assembling deflection delta L in release structure and to assemble the flexibility matrix delta, use standard methods known in structural analysis like this is you have to use conjugate beam method or unit load method. Generally the conjugate beam method is used in the continuous beam problem and the unit load method is used in the frame problem. So here by using the conjugate beam method we will solve one continuous beam problem. Coming to one problem, analyze the continuous beam shown in figure by flexibility matrix method. Take EI is constant throughout. So this is the continuous beam is given, 3-span continuous beam A, B, C, D, and the A is hinged, B, C, D roller supported, and the span length AB is given 12 meter and span length BC is given 12 meter and span length CD is given 12 meter. And on span AB there is having the uniform distributed load 40 kilonewton by meter, and on the span BC there is having the concentrated load at a distance 4 meter from the support B, and on the span CD there is having the uniform distributed load 20 kilonewton by meter, and the moment of inertia of AB is I and BC is I and CD is I. So this is 3-span continuous beam. What is the first step? So first step that you have to find out the degree of static indeterminacy. So in this case, what is the degree of static indeterminacy? Because this is the hinge support and this is roller support, roller support, roller support. So at hinge support there are two reaction component, and at the roller support there is one reaction component. Here one reaction, here one reaction, here one reaction, and here two reactions. So total number of reaction component is 5, but the available static equilibrium equation is 3. So what is the degree of static indeterminacy? The degree of static indeterminacy is equal to 5 minus 3, this is equal to 2. So you have to choose two redundant. So you have to assign two coordinate. Where you will choose the redundant? So you have to choose one redundant at B, and you have to choose another redundant at C. The moments at B and C are taken at the redundant force. You have to take the moment at B, one redundant force, and to choose the moment at C, another redundant force. Hence, the release structure is obtained by introducing the hinge at B and C. You will get the release structure by introducing the hinge at B and C. The coordinate direction are as shown in figure 2. So you have to assign the coordinate direction at the B and C, because here there are the degree of static indeterminacy of this problem is 2. So you have to take two coordinates, and you have to assign two coordinates at B and C. The first coordinate you have to take at B, and the second coordinate you have to take C, and you have to take the moment as a redundant force at B and C. So here this is the coordinate direction. So you have to give the this is the coordinate 1 at B, and this is the coordinate 2 at C. This is the direction of the coordinate at B and C. So you have to assign two coordinate. First coordinate is at B, and second coordinate is at C. Then what is the next step? So you have to find out the displacement due to the given loading in the release structure. Using the conjugate beam method, you can find out what is the displacement due to given loading in the release structure. So what is the load is given here? So due to this load, separately you have to draw the free bending moment diagram. Here what is the free bending moment diagram? Because this is the load is given 40 kilonewton by meter. So what is the free BMT head? So what is the maximum moment at the center? W L square by 8. Similarly, here there is having the eccentrical loading. So at a distance 4 meter from the support B and 8 meter from the support C. So what is the moment here at the loading point? W A B by L. W A B by L. W is equal to 120, A 4 and B 8 by L. So you will get the bending moment, free bending moment diagram is triangular, and here also there is having the UDL. So due to this UDL, the bending moment diagram is parabolic, and what is the maximum moment at the center? So this is equal to W L square by 8. So W is given 20 into L is given 12. So 20 into 12 square by 8. This is the moment. Here this is the parabolic, the bending moment diagram. Here the bending moment diagram is the triangle, and here the bending moment diagram is parabolic. So first you draw the free bending moment diagram of this continuous beam. Then the M by EI diagram is loading for the conjugate beam. So after getting the free bending moment diagram of this beam, then what you have to take? The bending moment divided by EI is the loading for the conjugate beam. So this is the parabola, the bending moment diagram. Here this is triangle, and here this is parabola. This is the conjugate beam for release structure. So what is the maximum ordinate here? So W L square by 8, 40 into 12 square by 8. So the maximum moment here 720. So and you have to divide by EI. So this becomes the loading for the conjugate beam. And here this is the triangular, the bending moment diagram here triangle. What is the moment here? W A B by L. W is given 120, A is 4 and B is 8 and L is equal to 12. So this is the moment at the loading point divided by EI. So this is the loading for the conjugate beam. So this is equal to 320 by EI. Maximum ordinate of load on A dash B dash is equal to 720 by EI, and maximum ordinate of load on B dash C dash is equal to 320 by EI. Similarly, what is the maximum ordinate of load on C dash D dash? Maximum ordinate of load on C dash D dash is equal to So what is the free bending moment diagram? So divided by EI is the loading for the conjugate beam, and here the load, here the maximum ordinate is W L square by 8. So W is given 20 and L is given 12, 20 into 12 square by 8. So this is the maximum ordinate and divided by EI. So this is loading for the conjugate beam. So here the maximum ordinate of load on C dash D dash is equal to 360 by EI. So these are the maximum ordinate of load on A dash B dash. This is maximum ordinate of load on B dash C dash, and this is the maximum ordinate of load on C dash D dash. And this is the conjugate beam for release structure. Then you have to find out what is the displacement due to the external loading in coordinate direction 1 and in coordinate 2. So you have to find out what is the displacement here and what is the displacement here. Here the displacement is delta 1L and here the displacement is delta 2L due to the given loading. So delta 1L is the displacement in coordinate direction 1. So this you can find out, here you see. So the displacement in coordinate direction 1 you can find out from this one and from this one. What is the reaction here? So in conjugate beam, you know, in conjugate beam method, when you want to find out the displacement in the real beam, so in conjugate beam you have to find out what is the shear force at the corresponding point. For displacement you have to find out what is the shear force at the corresponding section of the conjugate beam. So you want to find out what is the displacement at the coordinate 1. Here you have to find out what is the displacement at the coordinate 1 in real beam and what is the displacement at the coordinate 2 in real beam due to the given loading. So in conjugate beam you have to find out what is the reaction here from this one and what is the reaction here from this one. This total reaction is the reaction at the point B dash. So reaction at the B dash, this is equal to the shear at the B dash. This is in conjugate beam is equal to the displacement 1L in the real beam. So you can find out the displacement in the real beam. So you have to find out here what is the reaction from this one and from this one. So from this one, how you will find out the reaction here at B dash, because this is the parabolic loading, this is the parabolic loading and this is symmetrical loading. So what is the total load? That load is divided by 2 will be shared by each reaction component. This side RA dash RB dash is equal to the total area of this load divided by 2. So what is the total area of this load? What is the area? So this is parabola. So the area of the parabola is 2/3 into base into height. Base is given 12 meter and the height you know 720 by EI. 2/3 into 12 into 720 by EI divided by 2 is equal to the reaction here and reaction here. So RA dash, this is the reaction. This is the reaction. Here you see the displacement in coordinate direction 1 is equal to delta 1L, the rotation of AB at B plus rotation of BC at B. So this is delta 1L is equal to shear force at B dash in conjugate beam A dash B dash and shear force at B dash in conjugate beam B dash C dash. So you have to find out what is the shear force at B dash in conjugate beam A dash B dash, and you have to find out what is the shear force at B dash in conjugate beam B dash C dash. You have to find out what is the reaction, already I have explained. So you have to find out what is the reaction from this beam and you have to find out what is the reaction from this beam. Then the total reaction is the rotation at B of the real beam, the displacement at B in the real beam. So this is half into 2/3 into 720 by EI into 12. This is the reaction from A dash B dash. Similarly find out what is the reaction here. So for this reaction you have to take the moment about the point C dash. So RB dash into 12, RB dash into 12 is equal to what is this area, half into base into height, half into 12 into 320 by EI. And what is the central distance of this area from this end? So this is equal to, so what is the total length? 12 and plus 8, 12 plus 8 by 3. This is the central distance of the eccentrical triangle. So here half into 320 by EI into 12 into 12 plus 8 by 3 into 1 by 12. So, this is the reaction at B dash in span B dash C dash. So, what is the total reaction? This is the reaction from A dash B dash at B dash, and this is the reaction from B dash C dash at B dash. So, the total reaction is equal to 2880 by EI plus 1066.67 by EI. So, this total reaction at B dash, this is equal to the displacement in coordinate direction 1 due to the given loading. So, delta 1L is equal to the total reaction at B dash. So, that is equal to 3946.67 by EI. Similarly, find out what is the displacement in coordinate direction 2 due to the given loading. So, delta 2L is equal to rotation at C in BC plus rotation at C in CD. In real beam, you have to find out what is the rotation at C in BC and what is the rotation at C in CD. So, this is equal to delta 2L. Then delta 2L is equal to shear force at C dash in conjugate beam B dash C dash plus shear force at C dash in conjugate beam C dash D dash. You have to find out this is the coordinate 2. So, you have to find out, so for this you have to find out what is the displacement in coordinate direction 2 delta 2L due to the given loading. So, what you have to do? So, here you have to find out what is the reaction RC dash from this span, and you have to find out RC dash from this span. The total reaction is the shear force at C dash in the conjugate beam, and that is equal to the displacement in coordinate direction 2 of the real beam. So, here you have to find out what is the reaction, and here you have to find out what is the reaction from this span. So, from this span, so what is the reaction here? Because this is the parabola, and you have to take the total area of the parabola 2/3 into base into height, 2/3 into 12 into 360 by EI. So, and half of this area is shared by each reaction component. So, RC dash RD dash is equal to half into 2/3 into 12 into 360 by EI. You can find out the reaction here. Then from this span you have to find out what is the reaction here. So, for this reaction, because this is the eccentrical loading, so here this is if the area is symmetrical, then that case the half of the area is shared by each reaction component, but this is the eccentrical. So, here you have to take the moment about this point, you have to take the moment about B dash, and you have to find out what is the reaction here. So, by taking moment about B dash, here you have to take RC dash into 12 is equal to half into 12 into 320 by EI and the centroidal distance, and the centroidal distance is equal to 12 plus 4 by 3, and from this relation you will find out what is the reaction at C dash from the span B dash C dash. This is delta 2L is equal to half into 12 into 320 by EI into 12 plus 4 by 3 into 1 by 12. This is the reaction at C dash from B dash C dash, and this is the reaction at C dash from the C dash and D dash span, C dash and D dash span. Half into 2 by 3 into 12 into 360 by EI. Then after simplification, so we will get delta 2L is equal to 853.33 by EI plus 1440 by EI, then delta 2L is equal to 2293.33 EI. So, this is the displacement in coordinate direction 2 due to the given loading. So, here you got what is the displacement in coordinate direction 1 due to the given loading using the conjugate beam method, and what is the displacement in coordinate direction 2 due to the given loading using the conjugate beam method. Simply you have to remember, when you want to find out the displacement in real beam, so in conjugate beam you have to find out what is the shear force at the corresponding section. For rotational displacement you have to find out in conjugate beam, that is the shear force, and for the vertical displacement you have to find out in conjugate beam, that is the moment in the corresponding section. Because here you are taking, this is the rotational displacement, so you have to find out what is the shear force are the section in the conjugate beam. Then coming to the flexibility matrix, by using the unit force in coordinate direction 1 and 2, and you have to find out what is the displacement at coordinate 1 and what is the coordinate 2, because here you are choosing two coordinate, one coordinate is at B and another coordinate is at C. So the coordinate at B, the coordinate is 1, and at C the coordinate is 2. So first you apply the unit force in coordinate direction 1. Due to the unit force, you have to find out what is the displacement at coordinate 1 and what is the displacement at coordinate 2, delta 1 and delta 2 1. This is the unit moment, because you are taking the moments as a redundant, so you have to apply the unit moment here. Unit force is applied in determinate structure in coordinate direction 1 as shown in figure. This is the figure, this is the unit force. Release structure with unit load in coordinate direction 1. So this is due to this unit force, unit moment. So what is the bending moment diagram? Because here 1 kilonewton meter and here this moment is 0, 1 kilonewton meter. Similarly here this is 1 kilonewton meter and here 0. So this is the bending moment diagram. This is the bending moment 1, 0 and here 1 and 0. Then you have to divide by EI. So 1 by EI is the loading for the conjugate beam. This is the loading for the conjugate beam. You have to divide the bending moment by EI, and that becomes the loading for the conjugate beam. So 1 by EI is the loading for the conjugate beam. So this is the support A dash, B dash, C dash. Here you take the for real beam A, B, C, D, and for conjugate beam you take the support A dash, B dash, C dash and D dash. So here A dash, B dash, C dash, D dash. So what you have to find out? You have to find out delta 1 and delta 2 1. You have to find out the displacement at coordinate 1 and displacement at coordinate 2 due to the unit moment in coordinate direction 1. Due to this unit moment or unit force, you have to find out what is the displacement at coordinate 1 and what is the displacement at coordinate 2. Delta 1 so delta 1 is equal to shear force at B dash in conjugate beam A dash B dash plus shear force at B dash in conjugate beam B dash C dash. So you have to find out what is the shear force here or what is the reaction here and what is the reaction here. From the A dash B dash you have to find out what is the reaction here, and from B dash C dash you have to find out what is the reaction here. Total reaction at B dash is equal to the shear force B dash, and that is here equal to delta 1 delta 1 So delta 1 is equal to RB dash is equal to reaction at B dash in conjugate beam A dash B dash plus reaction at B dash in conjugate beam B dash C dash. So delta 1 is equal to RB dash. Then find out what is the reaction here by taking the moment about this point. You can find out what is the reaction. RB dash into 12 is equal to, this is the triangle. So what is the area of the triangle? Half into 12 into 1 by EI. And what is the central distance? So this is equal to 2/3 into 12. Then after simplification you will get what is the reaction at B dash, RB dash from this span. Similarly from this span also you can find out what is the reaction at B dash by taking moment about C dash. RB dash into 12 is equal to half into 12 into 1 by EI, and what is the central distance? The central distance is equal to 2/3 into 12. So here you get what is the reaction from the span B dash C dash. Then simplifying, the displacement at coordinate 1 due to unit force at coordinate 1, that is delta 1 is equal to 8 by EI. Similarly find out delta 2 1. Delta 2 1 is equal to shear force at C dash in conjugate beam B dash C dash. Delta 2 1 is equal to reaction at C dash in conjugate beam B dash C dash. So delta 2 1 here you have to find out. Here you have to find out, this is the coordinate 2. So here you have to find out the reaction at C dash. Here there is no loading, only you have to find out what is the reaction at C dash from this span. So you have to take the moment about the point B dash. So RC dash into 12 is equal to what is the area, half into 12 into 1 by EI, and what is the central distance, So this is equal to 1 by 3 into 12. Then you can find out what is the reaction here. So this reaction is the shear force at C dash, and this is equal to the delta 2 1. So delta 2 1 is equal to RC dash is equal to 1/3 into 1 by 2 into 12 into 1 by EI. So this is equal to 2 by EI. So delta 2 1 is equal to 2 by EI. Then apply the unit force in coordinate direction 2. Then apply unit force in coordinate direction 2 as shown in figure 6. This is the unit force in coordinate direction 2. Unit force, that is the unit moment. Unit force is the unit moment. You have to apply in coordinate direction 2. Similarly, you can draw the bending moment diagram, and the M by EI diagram is the loading for the conjugate beam. So this is the bending moment diagram 1 1, because this is the unit moment here, So this side moment 1, this side 0, and this side moment 1, and this side 0, and the moment by EI is the loading for the conjugate beam 1 by EI. Similarly, here you have to find out what is delta 1 2 and delta 2 2. Due to the unit force at coordinate 2, you have to find out what is the displacement at coordinate 1 and what is the displacement at coordinate 2. So the displacement at coordinate 1 due to the unit force at coordinate 2, delta 1 2. Similarly, what is the displacement at 2 due to the unit force at coordinate 2? This is delta 2 2. Similarly, you can find out delta 1 2. So you have to find out what is the reaction here from this one. R beta is equal to 1 by 3 into 1 by 2 into 12 into 1 by EI. This is equal to 2 by EI. Similarly, you have to find out delta 2 2. So delta 2 2, you can find out what is the reaction RC dash from this one and RC dash from this one. The total reaction is the delta 2 2. Delta 2 2 is equal to RC dash, and this is the reaction from the span B dash C dash, and this is the reaction from the span C dash D dash, and this is equal to 8 by EI. So delta 2 2 is equal to 8 by EI, and delta 1 2 is equal to 2 by EI. So here you got delta 1 1 and delta 2 1, and here you got delta 1 2 and delta 2 2. These four flexibility coefficient become the flexibility matrix. Then you know the final displacement at 1 and 2 are zeros. The final displacement at 1 2 are 0, because from the question here there is no displacement takes place at B, and here also there is no displacement takes place, because the supports are having at the same level. So the final displacement at coordinate 1 and coordinate 2, that is your equal to 0. The final displacement at 1 and 2 are 0. Hence the flexibility equation is given by, this is the flexibility equation, del into P is equal to delta minus delta L. So del is the flexibility matrix. Already you got delta 1 1, delta 1 2, delta 2 1, delta 2 2. This is you already got the flexibility matrix, and this is the redundant. You are taking two coordinate, that is the redundant at coordinate 1 is P1 and redundant at coordinate 2 is P2, and this is the final displacement at 1 and 2 0 0, and this is the displacement due to the external loading. Already you got due to external loading what is the displacement. Then this is the expression. You have to put here the value delta 1 1, delta 1 2, delta 2 1, delta 2 2. Then after putting this is the expression. Then this is the expression. You take here common 1 by EI 8228 P1 P2 is equal to 1 by EI minus 3946.67 minus 2293.33. Then 1 by EI cancel. Then find out what is the P1 P2. This is the inverse of the flexibility matrix. This is the flexibility matrix. So take this flexibility matrix this side. So here you will get the inverse of the flexibility matrix, and this is the column matrix. This is the column matrix. So first you take the inverse of the flexibility matrix. This is the column matrix. Then multiply these two matrix. Then you get what is the redundant P1 and P2. So finally the redundant P1 is equal to minus 449.78 and P2 is equal to minus 174.22. So here you are taking the redundant, the moment at the support B, and the moment at the support C. So this is the moment MB at the support B, and this is the moment MC at the support C. So MB is equal to P1, this is equal to minus 449.78. Here you see, here you got the negative sign, negative, and here the direction of the coordinate, here you have given the direction of the coordinate. This side is anti-clockwise, this side is clockwise. Here this is anti-clockwise, this side clockwise. But you got here the P1 is equal to minus value and P2 is equal to minus value. So just to change the direction of the coordinate. Here this side is your anti-clockwise and this side clockwise, and here also this side anti-clockwise, this side clockwise. Just change the direction of the coordinate, because here you got the negative value. That's why you change the redundant force direction. P1 minus 449.78, so but and P2 minus 174.22, but here you give 449.78. you change the direction of the coordinate. So this is the bending moment at B, and this is the bending moment at C, 174.22 kilonewton meter. And here you know the bending moment is 0, and here you know the bending moment is 0. And due to this moment, so this is the bending moment diagram. Due to the support moment, here you got two redundant, and that two redundant is the moment at B and moment at C. And due to here you know the moment is 0, and here you know the moment is 0. So due to this, here this is the fixed bending moment diagram. Then you know what is the load here, and you know what is the load here, and you know what is the load here. So due to this load, so this is the free BMT. Already you got 720 kilonewton meter, and here due to this eccentrical loading, the moment here 320 kilonewton meter, and due to UDL here, the bending moment diagram is parabolic. This is 360 kilonewton meter. Then this is the negative bending moment diagram. This is, and this is the positive bending moment diagram. Then after cancelling the positive and negative portion, this one and this one and this one, and this is the final bending moment diagram. This is positive, this is negative, this is positive, this is negative, and this is positive. So this is the final bending moment diagram of the 3-span continuous beam. So after getting the redundant, then you can give the direction of the moment. Then after giving the direction of the force, then you can draw the bending moment diagram. So from the support moment, you can draw the negative bending moment diagram, and from the what is the load given, and due to that load you can draw the free bending moment diagram. Then after combining these two positive and negative bending moment diagram, you get the final bending moment diagram. This is all about the analysis of 3-span continuous beam using the flexibility matrix method. Now all are clear how to solve the 3-span continuous beam using the flexibility matrix method.